Bismillahirrahmanirrahim. Welcome back to my channel. I'm back with a video on software on antennas. So recently, I think I made a short video on it. This is the antenna that I received from China, a PCB-based antenna, FR4-based antenna that's supposed to operate from 2.35 gigahertz all the way up to 2.55 gigahertz. It's a Yagi antenna. I'll walk you through it, and it's a directional. Yagis are generally a directional antenna. It has a gain. Advertised gain is about 10 dB. So let's quickly look at this. So this is the back of the PCB. This is the front of the PCB. Why am I saying it's front of the PCB or back of the PCB? Is due to the connection. As you know, in Yagi antennas, you have a lot of elements. You have one dipole antenna, then you can have one element which is actually being energized while the rest of the element are parasitic. And you can clearly see that the connection is firing up this dipole. None of the elements are physically connected. They are just placed apart with some distance of lambda by 4. And let's look at the other side of the PCB so you can clearly see this. So this is your folded dipole, which is connected. This is the only element that is being fired. All of these rest of these elements are just parasitic elements. On the back of your folded dipole, this thing is known as a reflector. Whatever the energy that is being radiated, it's going to reflect, it's going to hit this reflector, and it's going to try to push it up. These three elements are called directors. As you can clearly see, whatever the length of your Yagi antenna or dipole antenna is this element is going to be at least, in different books is different thing, but normally 5% more than your half-wave dipole antenna. In this case, this is a folded dipole antenna. These three are acting as directors. This is going to direct the energy. If you forgot about the directional pattern of your dipole antenna, half-wave dipole antenna is basically an H shape. So if this antenna is generating an H shape like this, whatever the energy is being hit on the back of it, this reflector is going to push it up, and that pushing it up actually making this antenna being a directional antenna. So this antenna is about 100 years old. I mean, the concept of this antenna is about 100 years old. So let's quickly check this antenna and let's see what we can find using our VNA. So let's just quickly look at it. Let me just plug it in to my VNA, or at least let me try to plug it in. It's screwed on. Alrighty. So let's look at our S11. So this is my S11. This looks really, really nice. Let me move my marker. I already have my marker on. So 2.35 is the starting frequency. So let's quickly go to 2.35. All right, 2.35 is somewhere over here. So right here. So according to our VNA measurement, this is not very well because you're getting about -8, and according to our rule of thumb, anything less than -10 dB is good enough. That's the rule of thumb in RF. And when it comes to antennas and RF equipment or RF component, so -10 dB is good enough. But okay, 2.35 -9. I can see because of my connector and the losses, and my VNA is not like, it has about 1 dB of calibration up and down. Plus and minus error. Okay, 2.35 is about -9, and let's put it at 2.35. So let's bring another marker in. So let's call it another marker. Let's bring marker number 2. All right, so let me bring my marker number 2. All right, so let's bring my marker number 2 and put that at 2.55 gigahertz. All right, let's see. Let's bring it over here. So about 2.3555 megahertz right here. Right here, -11 dB. So this is quite good. And I think based on that, they're calculating the bandwidth. So 2.55 minus 2.35. That's the bandwidth that you're getting. That's the thickness. This thickness, the width. Let's bring in another marker. And let's see, where do I see another dip? Another dip is somewhere around here. That is about -11 dB at 4.65 gigahertz. All the rest of the other places, this antenna is not operating. I can do a couple other measurements. Of course, this is a single port device, so you'll be only able to measure S11 and S22s, and I believe S11 and S22 should be exactly the same thing. Why? Because when you connect it to your S22, because right now I've connected to port 1, S22 is just the same thing. So it's a single port antenna device. Let's make another measurement. Let's do some impedance measurements. Let's do the S11. So wherever I had my marker, so about 2.35 gigahertz. So wherever my marker was, which is right here. At this point, I was getting about what, 73 ohms of 2.55. I'm getting about 77 ohms of impedance. Let's say, where do I get my 50 ohms? So at 50 ohms, if I want to get a M2 of 50 ohms, I should go about 2.51 gigahertz. And let me just look at my marker number 1 now. If I want to get 50 ohms, I should go to at about 2.37. So at 2.37 gigahertz, I will get about 50 ohms. At 2.1, so this is like perfect. Like you want to get this measurement to be exactly perfect. So this was the frequency of operation, 2.7, 2.37 all the way up to 2.51, which is a very good frequency range because this is the range where your 2.4 gigahertz antenna operates, where your Wi-Fi operates. So it is covering this with perfect impedance matching of about 50 ohms, as you can clearly see here, and as you can clearly see here. So anything between 2.3 and 2.51, it's perfectly fine. I mean, you're getting good impedance matching. All right. I can also make some other measurements, like for example, I can do Y measurement as well. So if I want to look at my Y measurement, so 21 point, because I had the marker set, so 21.20, as you can clearly see, not clearly see, I'm going to read off from my VNA, 21.24 millisiemens, and if I were to take an invert of that, I would get about 50 ohms. I can make some other measurements. For example, let's look at my S11 or ratio. My parameters. All right, let's see what else I can measure. I always forget where do I have to go and get my SWR. Here we go. So SWR is, okay, I need to fix this scale, because normally last time the same thing happened, and I need to fix this. Just give me a minute. There we go. Because this, when the scale is not properly fixed, I mean, this is what happens. It actually right at the very like bottom level out. So M1, you're getting about an NSWR of 1.043, and at M2 1.041, which means exactly that it is perfectly, because SWR is basically 1 plus reflection coefficient divided by 1 minus reflection coefficient. Whenever you have a perfect matching, you will always get about 1 of SWR. This is what I want. And having a 2 SWR means that at least 50% is going to my load, or being connected. 50%, at least 50% of the power is going to my load, 50% is being reflected. So having an SWR of 1, that is like showing that it's perfectly matched. There's nothing going coming back to my system. No reflected waves are coming back to my system. So that's the idea behind this Yagi antenna video. And I hope if you have any questions, leave it in the comment section. And please don't forget to like and subscribe to my channel. And thanks for watching.